You know when your phone magically finds a face in a photo? Ever stop to wonder how it actually does that? Well, today we're going to decode the magic of computer vision. And our guide for this whole thing is something you would probably never expect: a university final exam. I mean, how does it really see? How does a machine go from a bunch of random pixels to recognizing your face, a cat, or a car? It feels like it shouldn't be possible, but the logic behind it is just fascinating. And believe it or not, all the big secrets are laid out right here in this computer vision exam from a university. Now, I know it looks super intimidating, but we're going to use it as a kind of treasure map to understand how this all works from the ground up. So our journey is going to start at the very beginning. We're going to follow the exact steps a computer takes to make sense of the visual world for the very first time. Okay, so before a computer can do any of the cool stuff, it has to get over one massive hurdle. How do you take a picture, something we see with our eyes, and turn it into a language that a machine can actually understand? Right, so we look at this image from the exam paper, and our brains just instantly get it. It's a cat, there's some grass, different textures. For us, it's totally effortless. But for a computer? Oh, it's not a cat at all. To a computer, it's this: a huge grid of numbers. Each one of those numbers just represents a tiny little dot, a pixel, and tells the computer how bright that specific dot is. That's it. That's the raw data. And this really shows you the fundamental translation at the heart of all computer vision. The rich visual world that we see on the left becomes the structured mathematical world a computer can actually work with on the right. This one step, turning light and color into a spreadsheet of numbers, is the foundation for everything that comes next. And it all boils down to this one thing: the pixel. The best way to think about it is like a single tile in a giant mosaic. Millions, sometimes even billions, of these little numbered tiles come together to build every single digital picture you've ever laid eyes on. Okay, so the computer has its massive grid of numbers. Now what? That's just a bunch of data. The next big challenge is, how does it start to find any meaningful shapes inside all that numerical chaos? It's a real puzzle, right? I mean, that sea of numbers looks like pure static. The computer's next job is to find the hidden structure in there, like the actual outline of the cat's face. And the solution is a process called edge detection. Our exam paper actually points to a famous one in question 5B, the Caney edge detector. These algorithms are designed to do one simple thing: scan that whole grid of numbers and find the exact spots where the values change really suddenly. A sharp jump in numbers almost always means a visual edge in the real world. And the result is pretty striking. By finding all those edges, the computer essentially creates its own line drawing of the original image. It just strips away all the complicated stuff like color and texture to focus on the one thing that matters: the fundamental structure of the object. It's like a coloring book outline. Now, an outline is a great start for sure, but it's not really enough to reliably identify something in different photos or from different angles. For that, the computer needs to find more unique, more stable landmarks. And that's where clever methods like SIFT come in, which, yep, is also mentioned in question 6A of our exam. Think of it like this: the algorithm scans the image and finds interesting points, like the corner of an eye or a unique little pattern in the fur. Then it creates a super detailed numerical description for that tiny spot. It's basically a fingerprint. Then it can go and look for that exact same fingerprint in other pictures. So we've got the numbers, we have the edges, and we've got these unique fingerprints. Now it's time for the final leap: putting it all together to actually recognize what's in the picture. This whole process, this is the goal of object detection. It's not just about being able to say, there's a cat in this photo. As we can see from the exam questions, it's also about being able to say, and the cat is right here. So let's circle back to our cat. The computer has analyzed the edges, it's found all the key feature points. So what does it have to show for all that work? What's the final output? The final result is a bounding box, and that's a concept pulled directly from question 5B on the exam. The algorithm uses all that data it's collected to confidently draw a box and declare, the object that I've identified as a cat is located right inside these coordinates. Pretty cool, huh? And of course, this applies to way more than just cats. The exam also brings up a classic method for facial recognition called eigenfaces. And it works on the exact same principle, breaking a human face down into a combination of essential features, which can then be identified and recognized again later. So, why does digging through an old academic exam paper even matter? Because these concepts that seem so abstract, they're the literal foundation of technology that we all use every single day. Seriously, think about it. Every time your phone's camera blurs the background for a portrait photo, that's edge detection at work. When you get a suggestion to tag a friend on social media, that's object detection. From self-driving cars navigating roads to the silly AR filters you use online, these principles are absolutely everywhere. And really, that's the key takeaway. What starts out as a complex mathematical problem on an exam paper is what ultimately becomes the seamless, almost invisible technology sitting in your pocket. We've just walked through the fundamental building blocks of how machines learn to see our world. And that kind of leaves us with a final thought to chew on. We've seen how it all works, but as this technology gets exponentially better at seeing and understanding our world, what are the next great challenges and the next great opportunities that are going to pop up?